Should I talk here or here?
I think that it's fine, whatever you want, you can do it. And if you want to hang it.
No, okay. Good.
Oh, wait.
So we're going to get going here. I'm Steve Lund, and I'm helping, I guess, moderate the session. This is the session on behavior analysis. We have 4 papers, 3 of them short, 1 long. The first one will be on multimodal learning analytics with Paulo Blikstein.
Okay. Hello. I don't think it's on. Okay. Hello. Today I'm going to talk about multimodal learning analytics, and since my student Marcelo will talk immediately after me, this will be an introduction to many things we do around this area, and then he will go deep into one of the cases that I will introduce here. So what is multimodal learning analytics? So first let me give you some context about what this is and why it's needed. So, you know, from the classic literature on constructivism and constructionism and motivation theories and all kinds of things like that, we know that learning is social, is mediated, is multimodal, a lot of emotional aspects, physiological aspects, and developmental aspects go into learning. But what we can capture in a computer screen when students are interacting with computer-based environments is just a small part of all those things we know about learning, especially in particular how learning is social, because when you're interacting with just a computer screen, you're not interacting with other people face-to-face. And also, you're just capturing one channel of communication, which is students looking, visually looking at things at the computer screen. You're not capturing how their bodies are moving, how they're talking about things, their facial expressions, and all kinds of things like that. So multimodal learning analytics is an attempt to, it's a subfield within learning analytics that we've created to look at all those other modes of data capture that are not normally captured when you only look at the interactions with the computer. So I'm particularly interested in environments like this. So we have a project called Fab Lab at School, where we build digital fabrication labs in schools, and you might have heard of the maker movement and maker spaces and all kinds of things like that. So I'm interested in using learning analytics techniques to look at those kinds of places where kids are building things, physically building artifacts and things like that. So the problems with those kinds of environments is one problem is that assessment is a big bottleneck. So it's hard for teachers to monitor what 20 kids are doing in a maker lab and doing project-based things and all of that. It's very hard to know who is doing what and who is actually learning and who is just doing what they already know how to do. And research in those environments is very laborious. It's very hard because for each child you need a researcher kind of shadowing and collecting data and transcribing data. So it's a very slow and laborious process. And to assess, to address both of those things, you know, we came up with this idea of multimodal learning analytics, which is using machine learning, computer vision, and normal qualitative methods, but infusing the learning analytics techniques into those qualitative methods to get more automaticity in the research results that we get, and also to offer teachers more ways to detect, diagnose, and assess learning. So one of the frameworks that we came up with was this idea of emergent markers of expertise. So imagine that, you know, when you're building one of those artifacts there, like the Da Vinci machine or something like that, you don't really know how expertise manifests itself. You know, of course, you can look at, like, you know, maybe an engineering course and see the kind of formalized way that engineering expertise manifests itself, but we don't really know if it, how exactly it happened. So what we try to do is, okay, let's actually, you know, forget those kind of formalized descriptions of engineering expertise, and let's interview and capture data from experts, from novices, and from intermediates. And let's see what kinds of multimodal behaviors they exhibit that we can associate with their expertise. So, for example, the way they talk about their constructions, the way they gesture, the way they actually build things. And let's imagine that when a child is going from being a novice to an expert, they will exhibit those behaviors that we captured before by, you know, interviewing and collecting data from those three groups. We'll see those behaviors pop up. We see the expertise emerge in different parts of that trajectory, and then we'll be able to tell if this child is learning, even though we don't know exactly how expertise looks like in that particular field. So we look at things like how the argumentation, so how they talk about their projects, certainty, how certain they are about what they're doing, about the results that they're getting, and other things that I'll explain a little bit, like adaptive expertise and things like that. So the idea is, first we collect the baseline data on expertise, looking at people from, you know, high school students to PhDs in mechanical engineering. We build a baseline of expertise along multiple dimensions, speech and gesture and constructive behavior and all kinds of things like that. And then we use that framework to assess students in those labs if they are evolving along those same lines. Okay, so some examples of this that I'll talk today is constructive behavior, so how do people build things, exploratory behavior, how do they explore a new environment, adaptive expertise, text mining things, so how, you know, we look at speech and how people talk about their projects, and tinkering and planning. So if people are, for example, programming, building a computer program, do they plan before they code? Do they just go along tinkering as they go, and all kinds of things like that? So those are some examples of things we explored, and what I will do in the next 10 minutes is to give examples from projects that we've done. So, you know, I can't go deep into each of the projects because I want to give you an overview, and then Marcelo will give you a more in-depth example of one of those things. So you see that I'll go fast on the example, so, you know, don't feel too unsatisfied with the level of detail that I'll be able to talk about, but the idea is really to just give you an overview, and then you have a chance to look at something more in depth. So one example is what we call constructive behavior. So here we put a subject in our lab, and we collect all kinds of data, but in this case, we are collecting video from, you know, they're building some kind of structure. In this case, they have to build a sort of a tower using different household materials like sticks and tape and things like that. And in this case, we're also capturing their gesture using a gesture sensor, as you can see. Sorry. So, you know, we're capturing the video and also the gesture, and then you see that, you know, we're overlaying them, but we can. So from the gesture capture, we can get a lot of interesting data about how much they're moving, how much they're reworking what they do, and all of that. But let me talk about a simpler case, which is just looking at the video of what they do and trying to interpret the different things they do. So we came up with, you know, after looking at many people are looking at those videos and all that. We have a code book for different types of actions that they can do. So you can see building, prototyping, undoing, system testing, organizing, breaking, adjusting, all kinds of things like that. So this is what emerged from coding those videos manually, like humans coding the videos. And then we use different techniques to look at several subjects. And one of the interesting things we found was that there was some interesting and marked difference between experts and intermediates and novices. For example, you can see that novices, they adjust. The thing they do the most is adjust, whereas experts, they think they do the most is build and test the system. So this is one example of how we can discover patterns that different people from with different levels of expertise have when they are doing a completely open-ended task. So we do coding of the videos, and then we reapply that coding to other data sets, and then we can build this baseline that we can use to understand how people evolve throughout one of those workshops that I mentioned before. And this is exactly what Marcelo will talk about, so I won't go into much detail about that. Another one is adaptive expertise. So how do people develop techniques to become more efficient at what they do? So let's look at quickly this video of, so this is two students. One is an expert, a mechanical engineering student. The other one is a literature major. They're trying to design a trash separation system, right? So let me just play it for a few seconds. So one thing that you should have noticed by now is that the expert, he barely drew anything, while the novice was like building all kinds of people and things like that. So what he did first was to build a table of properties of materials, right? And then he went to design a system when he knew exactly, the properties of paper and glass and metal and all of that. And then he knew that some of them had to float, some of them had to sink and all of that. So this is one of the classical, things in adaptive expertise, is that experts, they build tools, cognitive tools, to help them solve the problem. And then indeed, when we look at, the data from several subjects, we see that experts, they use those kinds of tools a lot more than novices, right? So the idea, again, is that if we see a novice starting to use those kinds of tools in the same way that experts do, we can tell that they are learning something. They are acquiring an expert behavior throughout the activity. So let me give you a couple of more examples. So this is a game, engineering game, where kids have to build gear systems. And in this case, we used eye tracking to look at how they were doing things differently. So you can see that when we did eye tracking, we clustered it. We did some machine learning here that I won't go into detail, but basically the difference between those three groups, and we got those differences in different kinds of groups, is that the first group, which got to the higher level of the game, of this engineering game, the first thing they look at is not like they look at the components that they have to work with. They have a lower time for the first fixation, so they immediately see what's important in the environment. Lower number of clicks, so they don't go like click happy, clicking on every single thing. They know where they should click. More unique fixation points, so they know where to pay attention, and more duration per fixation. And all of those things in the literature, they're correlated with cognitive ability and attention and all kinds of productive learning behaviors. So this was eye tracking, a different mode, yet a different mode of data collection. And finally, the tinkering and planning. So this was not like a physical task, but this was students programming on the computer, and we capture snapshots of every single time they saved or compiled their code. So for each student, we have like almost 2,000 snapshots of what they did. And then we end up with some kind of waveform like this in one of the analyses we do for the number of lines of code that they add or delete or all of that. So this is what we call like activity posts. So it's related to how much they add, how much they subtract, how much action they are doing in the. And then we compare, for example, their final assignments with the first assignments to see if they're evolving over time. If the kind of waveform that we get in assignment 3, which is one of the last ones, if it's similar to assignment 1 or assignment 2, so meaning if the last one is the same kind of post as the first, it means that they didn't learn much. They didn't go through the assignment 2 stage. If it's assignment 2 is similar to assignment 3, it means that they are progressing in a more linear fashion. And then when we look at their test scores, the group that got stuck in assignment 1, in the waveform of assignment 1, they performed significantly lower than the group that actually evolved over time. And another interesting result that we got is that students who transition from, if you imagine the waveform going from very large amplitude waves to very small amplitude waves, so students who add and delete big chunks of code versus students who add and subtract code many times. So if you transition from making big to small updates, so you're becoming a sort of a tinkerer, your score is lower. If you transition to doing larger updates, which will relate to more planning, so you're not like just adding little bits of code, but you're planning before adding, you get, that group gets a higher test scores. So I gave you a bunch of examples of this kind of work, and now I just want to leave you with this, because I have to stop, and then Marcelo will pick up from here, which is, so why are we doing this? So first thing is, we teach what we measure. That's, we know how schools work. So no fundamental change in education will come without advances in assessment. So if we keep assessing the same things, we'll keep sending the message to school that those things are important. And since there is an extensive literature on the benefits of hands-on learning, experimental learning, dealing with physical objects and all of that, this presentation and our work is a call for this community to broaden the kinds of learning that we care about and the kinds of data that we collect, and to care more about the physical world and the kinds of data that we can collect from students interacting with physical objects, building things, making things, constructing things. Because we know that there is extensive documentation on the benefits of that kind of learning. But because we deal with big data in this conference, it's a lot cheaper to collect computer data, because you can collect lots and lots of data. As you might have imagined from what we do, it's very hard work to collect all these videos, to code and all of that. But doing that work, I think, is important, because we send a message to educators and to students and to schools that we care about that kind of learning as well, and not just learning that where the student is in front of the computer all the time. So thank you, and now Marcelo.
We have time for a couple of questions.
Carlos Monroy from RISE. I'm glad that you brought this kind of analysis on this type of activities, because we have a blended learning environment, and we know that this is for a science curriculum. And so the experiments, the activities that the students do on a regular basis are kind of like the ones you describe here, and which are very important for the science learning that they do. So, and the challenge is how to capture that kind of activities and data. So my question is, so I saw some, you were recording some video about the activities that requires also instrumentation and equipment to do that. What would be a way that you see as feasible to make it more, like much easier to capture that kind of activities?
I think the quick answer to that question is that a lot of the, research normally in the beginning is expensive and hard, but over time we develop cheaper ways to do the same things. And fortunately, all this like sensing and video equipment and all of that, it's becoming a lot cheaper, and it's actually most of it is in your cell phone. So the gesture detection, for example, uses a $100 Kinect sensor. A lot of the things that we used to need, like $100,000 cameras and all of that, we can do with normal cameras. So I think this will be, if we develop the methods and the software to do this, I think the actual hardware will be, very inexpensive in the near future. And if we create a market for that, I think it will happen. But right now it's hard because we're just starting it.
Is it on? Okay, hi. I liked a lot the multimodal connection to expertise. I think the connection to expertise is really neat. I guess you've read Mickey Chi's work on the problem sorting, differences between expert and novices, and how she gets at conceptual change, conceptual development. I wonder if you've made those connections and some of her mechanisms for conceptual change if you're not going across the ontological boundary, that kind. But if you're within ontology, she has this kind of self-explanation effect. Might be neat to connect your kinds of activities with reflection and explanation, and see if if those things can intervene on development of expertise. So I don't know if you've thought about that sort of literature connection.
Yeah, no, I think that's definitely part of our inspiration to look at self-explanation. Actually, one of the setups that I didn't show is a multi-tabletop environment where kids, there is a camera and a microphone off that, and kids can explain what they're doing to others or to themselves to remember later and all of that. And then we compare conditions where they don't know there is a camera for them to explain and all of that, and conditions where they know, so they have to do self-explanations and all of that. And so I think that's a really important thing and a powerful mechanism that is known to help kids learn in that way. So it's definitely something that we care about. Yes.
Actually, I think we're on time for that one for questions.
And I guess as I'm finishing setting up, it is also something that we do. So we capture reflection and self-explanation from the students, sort of just periodically throughout their experience within the lab, and that's something that we also study and look at. Right. No, and I think that is part of what we try to incorporate within even the work that goes on there. PowerPoint just crashed, so I'll reboot real quick.